Welcome to Unit 6 of 11 CBSE Chemistry, focusing on equilibrium. This video will explore dynamic state architectures, chemical constants, factors regulating stress, and the mechanics of ionic systems. Dynamic equilibrium is a state where macroscopic parameters don't change, but forward and reverse processes continue at equal rates. It is a dynamic process attainable only in enclosed systems and is represented by opposing dynamic arrows. Equilibrium occurs in various physical systems. Solid-liquid equilibrium is at the melting point, where melting rate equals freezing rate. Liquid vapor is where vaporization equals condensation speed. Solid vapor is direct phase equilibrium, bypassing the liquid state, like the sublimation of iodine. Dissolution equilibria involves solutes in liquids. For solids, the dissolution rate matches the crystallization rate in a saturated solution. For gases, solubility is governed by Henry's law, which states that the mass of a dissolved gas is directly proportional to the gas pressure above the liquid. The law of chemical equilibrium, discovered by Goldberg and Waage, defines the equilibrium constant, Kc, for reversible reactions. This constant expresses the ratio of product concentrations raised to their stoichiometric powers over reactant concentrations at equilibrium. For gas phase equilibria, we use partial pressures instead of molar concentrations, leading to the constant Kp. The linking equation relates Kp to Kc using the ideal gas constant R, temperature T, and the change in moles of gas, $delta $n. Heterogeneous systems involve reactants and products in different phases. The active mass of pure solids and liquids is constant and factored out of the equilibrium expression. Le Chatelier's principle helps predict how systems will shift to counteract changes. The reaction quotient, Q, is used to predict the direction a reaction will shift to reach equilibrium. By comparing Q to the equilibrium constant $K_C, we can determine if the net reaction moves forward, backward, or is already at equilibrium. Le Chatelier's principle states that a system at equilibrium will shift to counteract any applied stress. For example, adding reactants shifts the equilibrium forward. Increasing pressure favors the side with fewer gas moles, and increasing temperature favors the endothermic direction. Ionic equilibrium involves acid-base models. The Arrhenius model focuses on H+ and OH- ions in water. Bronsted-Lowry involves proton donors and acceptors, establishing conjugate acid-base pairs. Lewis' definition covers non-protonic chemistry using electron pair donation or acceptance. The auto-ionization of water is quantified by the ionic product of water, $K_W. The Sorensen pH parameter, defined as the negative logarithm of the hydronium ion concentration, is used to express acidity and basicity. Ostwald's dilution law applies to weak electrolytes. The common ion phenomenon describes the suppression of a weak electrolyte's ionization when a strong electrolyte sharing a common ion is added, shifting the equilibrium. Buffer solutions resist changes in pH when small amounts of strong acids or bases are added. They consist of a weak acid and its conjugate salt, or a weak base and its conjugate salt. The Henderson-Hasselbalch equation calculates buffer pH. The solubility product constant, $K_SP$, applies to sparingly soluble salts. Comparing the ionic product, $Q_SP$ to $K_SP$ determines precipitation conditions. Precipitation occurs if $Q_SP$ is greater than $K_SP$. In summary, dynamic equilibrium shows microactivity despite macroregularity. The K value is temperature dependent. Le Chatelier's principle predicts shifts under stress. Buffer action and solubility properties are key to ionic frameworks. These are the sources used for the images and information in this video, including various chemistry resources and educational sites.